So thank you very much for having invited me to this prestigious conference, especially Mr. Chairman and all the organizers. Yeah, indeed, I am graduated in physics. Physics is the most hated subject taught in schools, also in universities, because it is boring, complicated, and useless. Of course, my vocation here, or at least professional task, is to a little bit discuss with this opinion, which is, in my opinion, a little bit wrong. Why should physics be, however, important and interesting? Because physics, explains natural phenomena, and we are surrounded by the natural phenomena. In ancient Greek, they use physis or physis. If there are some English-speaking people that may correct me which pronunciation is correct, physis. Yeah, physis. First time used by Homer in his Odyssey, and Hermes gives Odysseus a plant of moly and explains him, or the Odysseus, the physis of this plant. I mean, mechanisms of action of healing. So today the subject has a lot to do with symmetry. So start with a definition of symmetry as understood by physicists. In the eyes of physicists, symmetry is a collection of transformations or operations that leave the object invariant. Operations that leave the object invariant. So have a look at this square. This is a square. If I rotate square by 90 degrees or 180 degrees, 270 degrees, 360 degrees, it is the same. It becomes the same square. So there is a four-fold rotational symmetry marked by this small square in the middle. And then there are four different mirror planes. If we reflect this square, say, in this plane, we obtain the same square. Physicists, mathematical physicists, have developed a complicated but very useful so-called group theory, and this group of operations, symmetry operations, is known under the name of 4MM, but it is not so important. Now, the symmetry, of course, is present, if not ubiquitous, in architecture. Look at this building. This building is surely symmetric or invariant with respect to the middle plane. Huh? Surely it is the same after the transformation. So one example of symmetry as understood by physicists, invariance. Here is something local. I come from Kraków. In Kraków there is Sigismund Chapel, which shows evidently 8-fold rotational symmetry without counting mirror planes. So this is symmetry in art, architectural art. This is another kind of symmetry. I mean, translational symmetry. If we produce this tiling, we see that the same motif repeats in this plane. So this means that if I shift or I translate one tile to another, I obtain the same design. This is an ideally invariant object against translations, because any translation transforms it into the same thing. So it is some plane without texture or empty space. So here we speak of continuous translational invariance. Any translation, any shift in whatever direction whatever amount gives the same. Still, this kind of tissue. So to describe the symmetry of that, we often use a notion of so-called elementary cell. I mean, the motif that when repeated many times, all the times, will cover whole the plane with this pattern. The selection of the elementary cell is arbitrary. We can use different. Two kinds of elementary cells are depicted here. I told you symmetry axis, 4-fold axis, 8-fold axis, mirror planes, but these operations are spatial operations. They change space. But we can add other operations. Here, for instance, apparently this shape seems to be invariant against 100 degrees, 180 degrees rotation. Yeah, but black will become white, and white become well, and nobody will teach me what is white and what is black. So look, after this operation, we don't have the same object, but white and black have been interchanged. So what is this? But some symmetry is present here. So we say colored symmetry, and this is very often used in the physics of magnetism. That to spatial operations we add changes in color. Here we have only two colors, but more complicated groups also exist. Here, to be very exact, there are all the possible ways to tail a plane without voids. You can tile the plane with parallelograms, triangles, squares or rectangles. You cannot do it with pentagons. It is impossible to fill the surface without voids with only pentagonal shapes. Hexagonal is possible, 7 is impossible, 8, and nothing else. The only possible to tile the surface without voids is this. In the 20th century, there was an interesting question whether it is possible to tile the plane, but in an aperiodic way. I mean, that it wouldn't be repeatable by translation. And invention by Sir Roger Penrose was this, that if we have two different tiles, we can tile whole the plane without voids, and this is aperiodic. So it was rather famous as Penrose tiling. And just recent discovery, because for a long time people thought that it was the simplest way to do it. And this year, look, people. This is also interesting that with Penrose tiling we can have a fold axis, but the object should be finite, as you can see. But yeah, the discovery of this year is that we can use only one tile, and nevertheless to cover whole the plane. And interesting is the name of this, because people sometimes called it one stone tiling. In German, ein Stein tiling. So you see, it was a little bit complicated to invent the shape of this, very special. But it is possible to make a floor with these, but only one shape of tiles. What I'm going to speak today are textures, and textures are used in many applications. So engineers know textures, artists know textures, computer graphers, and all that. I'm most familiar with ferroic textures, but there are liquid crystalline glass forming wall canvas. Yeah, a texture usually come into existence as a result of spontaneous symmetry breaking. Spontaneous symmetry breaking. The problem started with Pierre Curie, the famous husband of Madame Curie, Pierre Curie published this work just several months before his wedding, and he writes very important phrase which is known today as a Curie principle. Here is this in his original language. When some causes produce some effects, the elements of symmetry of the causes have to be found in the effects. This is a Curie principle. Physics is an experimental science. This experiment may put into doubt the Curie principle. This object has an evident symmetry. There is a mirror plane going like that, vertical, and you see the left side, right side, like a Notre Dame cathedral has this symmetry. The cause is the movement of this stick, but I will try to put the stick along the mirror plane. So look what happens. In one moment, the symmetry disappears. The cause was symmetrical, but the result not. So something goes wrong. Mm-hmm. So nevertheless, people always say, especially material scientists, one more phrase from Pierre Curie, say that in spite of everything, the Curie principle is in power. And the idea is that if we had, please imagine that we have had many such machines to breaking symmetry. The machine was made for me by a genius from Institute of Nuclear Physics, Erasm Maria Dudkiewicz. So if we had many such machines, the probability of finding this wheel here would be equal. So this means that if we had many such things, the probability of symmetry breaking is the same, so the globally symmetry is preserved. Sometimes it is called that law of symmetry compensation. This is a notion from the international tables of crystallography. And now an example which arises from my collaboration with people with the Faculty of Chemistry, University of Wrocław. Thank you very much, the representatives, for having come. So you can follow if I correctly describe the problem. There is a crystal material which shows a so-called tetragonal symmetry. So the elementary cell, three-dimensional elementary cell, has a basis which is a regular square. We know already the symmetry of a square. Huh? And then, with a lowering of temperature, the square becomes rectangle with long axis here and short axis here. Moreover, this part goes right, this part goes left, which produces such a parallel pipette, which is no anymore cuboid. Huh? So you see this like that. So the symmetry of a square transforms in a symmetry of rectangle and also shifted like that. If you count it well, you will see that 4 possible variants. Therefore, the number, the letter V is used. Huh? Sometimes called also domains, can come to existence with equal probability. But you know, here is a square, rectangle, But this rectangle comes with the same probability. But this is impossible to find such rectangles in one sample, because here you see this edge is different than that. So it would be like a procrust that we had to change the dimension of that and of that to match them. So this is impossible. What we have to find so-called stress-free domain walls. Stress-free domain walls. So this is forbidden. But if we take two rectangles like that, fitted like that, you see that no change in shape is needed. The only problem is that the initial symmetry planes are now at different angle than initially. And there is a theory about that, but it is maybe not so important for you. But for you is what is important is the result, a texture. This is an example of ferroelastic texture, and you see that at high temperatures, the image in a polarized light, because the substance is transparent. If you enlight it with polarized light, it goes uniformly when it is this square phase, and with lowering temperature, the symmetry lowers, as I have shown you, and these domains appear that are different in brightness. And the final texture is very complicated, you see. It's reminds some parquet, and even have some relief of the surface. If you imagine that these colors correspond to some snow, if there is a green and red snow, so snow goes down, but here is some an edge, a ridge, like here. So this is, and all these angles could have been calculated, but by Paweł Sobieszczyk from Kraków. So, but of course we are visual artists, so this is the course of action. Initial state, high temperature, and when temperature becomes sufficiently low, this texture arises. And now we start from this low symmetry texture and raise the temperature, and we said that progressively the material changes to its initial state. This is an example of ferroelastic texture. These are people who contributed, who synthesized the material and who characterized it, just people from Wrocław. And here is the building of the chemistry faculty of Wrocław University. 2 days ago we had a lecture on liquid crystalline textures. I didn't attend it because I was in Dresden, so, but I am not specialist in that. But here you can see a collection of textures, also found in Institute of Nuclear Physics in cooperation with the Rzeszów University. And here, what you can see, you artists of course know this kind of decoration, which is called caelum stellatum. Caelum stellatum. I mean, the decoration of medieval churches. This is the vote of St. Mary Church in Kraków, just restored recently. So, of course, a modern artist may think of replacing this a little bit too schematic caelum stellatum with something like that, which gives some metaphysical depth. But I'm not an artist. Also in music we know notion of texture. If a composer starts to write his music, her music, usually he or she divides the time into equal intervals called measures. Which is very similar to crystallization in time, because time in our scale is almost continuous variable. Nevertheless, if we divide it into equal paces, it becomes translational invariant, but against only discrete number of measures. And look at that. What can happen usually, if you listen to a music, the rhythm is often very regular. Sometimes we can observe deviations from this regularity. So if we have more time, I will show you. This was, the rhythm was such that in every elementary cell we had four notes, 4 beats. But 5, 7 is rare. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah. This is rare, but happens. Especially in Balkan music. Also 5. So now this is what music theorists would call texture. This is a polyphonic texture, meaning that we have 2 parts or 2 voices, and the piece is constructed like in Baroque times. The main domain is called subject. Pa-da-da-dum, pa-dum, pa-da-dum. This is the subject. And you see that the same subject appears translated in different places, like a ferroelastic domain. However, some symmetry elements may be employed. This is called inversion in music, but for us it is just reflection in the horizontal plane. Ta-da-da-dum, ta-dum, ta-da-dum. This is this. We can also reverse time. Of course, it is impossible, but anyway, we can write the same notes from the end. Yum, ta-dum, ta-dum, ta-da-da-dum. And here is something interesting. It is a scale change in time. Every note is twice as long as in the original subject. So this is so-called scaling. Scaling, and in music, augmentation. So now the texture in its entirety. Johann Sebastian Bach composed 15 such inventions, 2-part inventions. This is what is called in theory of music polyphonic texture. It has to be contrasted with homophonic texture. Homophonic texture is characteristic for classical period, romantic period. So this is, and usually the primary form is sonata allegro. Sonata allegro has nothing to do with commercial activity. So, but these sonatas are usually very long, but we have no time. So this is a very short sonata. The texture relies on some evolution. So there is the theme, the first theme, which homophonic means that there is a principal voice accompanied by some chords. This is like it. Then there is a translation from initial key to the key fifth higher, which goes to transition, which goes to the so-called second theme, and then everything is ended and many times repeated. Then it comes what is called development, przetworzenie in Polish. Yeah? And after then, two subjects come together with the same key. It has been many papers on the significance and why should this form be so important. And the answer is because all the humanity consists of men and women. So this is a male theme, this is a female theme, which are in conflict at the beginning, but they unify at the end. Another explanation is from philosophy. I don't know whether this philosophy is mathematical or not, but anyway, dialectics. They say thesis, antithesis, and synthesis. Hegel, Marx, Engels, yeah. An example of homophonic texture. Repetition. Development. Recapitulation. We spoke on the symmetry transformations in this especially polyphonic texture. This is a motif invented by Ernst Mach, a physicist, and he is astonished. Why should this scripture, which is so symmetric against the reflection in the, it doesn't seem very symmetric. We shall see whether it sounds symmetric or not. And the problem is, maybe I will show you a solution. So here you see the waveforms of the same motif, but here as it is played, and here that this part is taken and reflected in the vertical plane. You see that it is symmetric and is not symmetric. The problem is that the beginning of a note is not equivalent to the end. So now some examples and a quiz even. Could you recognize the instrument which plays this this motif? This is time inverted. Can you recognize the instrument? Yeah, cello, but suppose string instrument. Yeah. The solution is, if I put it in a correct sense, you will have this. Maybe a different if I have this one and pulso. You know what is this? A wind instrument. Yeah. If I put it in a correct sense. So it is similar. There are some instruments that are time invertible. But if I take this, let me look at that. What instrument is it? Nobody knows. So if I put it in correct sense, a harp. So of course there are some instruments which are not invertible. So we have heard some days ago that time is not invertible. It's a very tricky thing, because there are some examples in physics that are equations that are invertible, but nevertheless not always. Maybe too specialized to go into the detail. This is a solution of this Ernst Mach problem. The solution is such that if you want to see the symmetry of ascending and descending notes, you have to put it to the equal rhythm. For instance, we have a banquet song. This would be symmetric, but maybe it's not so important. Of course, there will be discussion, private discussion are also. Yeah, this is something interesting, because here, once again, a substance from the chemistry faculty, which shows scaling invariance. You see a shape, the same shape, but in a different scale. So if you multiply all the coordinates with the subject, you will obtain something like that. So we are working on that. Professor Bator, of course, surveys of this, all the works. But if self-similarity exists in the realm of textures, you see that it's not so evident. Are the textures or growth of liquid crystals fractal? Because if something is invariant against scaling, it is usually fractal. The answer is yes, but mainly no. So a lot of things to be still needed, done. But so start from the oldest invented function which shows self-similarity. This is a Weierstrass function. Of course, people who can read mathematical formulae can imagine and can see that this function is invariant against a change of scale, because if I multiply t by b, I obtain, of course, here b to the power k plus 1, but this term already exists in the sum. So it is something, so an example, the last example. I have put this Weierstrass function and repeated motive 6 times. You see, it is repeated, but because of the invariance, self-similarity, some continuity is seen. So please sensate how it would sound. A sound which continuously descends. Is it possible? Of course it is impossible. But what I suggested to do is that find an example of symmetry breaking in the realm of self-similarity. I start with only one part of this Weierstrass function and add the terms in this series, and here is completely self-similar. So look and listen, listen this stat ma być. Gdzież jest to ten stat? To jest normal. Almost normal. Is it useful to analysis of the quasi self-similar object? I don't know. The time is almost over. Of course, we have to go into practice. Is it possible to write a piece of music which gives this constant glissando? This is my attempt. For two pianos. If you have musicians, we can speak on some performance. The rhythm of Krakowiak, of course, because I come from Kraków. Thank you very much, everybody, especially Sławek and Mateusz, who did an enormous effort. But it goes up and up and up all the time. Thank you very much for your attention, for your patience. Of course, you can put some more voices to the piece to make it more. And then discussion afterwards, private consultations. Thank you very much for your attention.
Piotr Zieliński. Right now, do you have any questions?
Thank you very much. I was wondering about the object that you called a subject in the musical texture, and it seems that this is an essential part of the work of art. And my question would be: are there any identity criterion for that that part? For example, because some of those subjects, the geometry is not the same. Let's say.
Geometry is not the same.
Yeah, but on what basis you could say that there is the same subject, and what is the identity criterion, if there is any?
Yeah. So the answer is very simple. How to identify the subject?
Yeah.
The subject consists of intervals between sounds. I mean, which is a logarithm of difference, logarithm of ratio of frequencies. Huh? This is like, and if it is shifted in pitch, so for me, if it is the same sequence of intervals is the same. But for people with absolute pitch, not. And this is very interesting thing for cognitivistic studies. Yeah, but for me, a sequence of intervals defines the subject.